Ever wondered how magnificent mountains and hard rocks gradually break down over time? It's all due to a natural process known as chemical weathering. This process is a geological superhero, silently shaping the world as we know it. It's the invisible sculptor of our planet's landscapes, transforming towering mountains into gentle rolling hills, and solid rock into fertile soil. Picture this: a rock, over centuries, enduring rain, heat, and wind. The water isn't just washing over it, it's interacting with the minerals, changing them from the inside out. That's chemical weathering in action, a silent and slow yet immensely powerful process. It's not just about shaping landscapes though. Chemical weathering plays a crucial role in soil formation. It breaks down rocks into smaller particles which mix with organic material to create the rich, fertile soil that sustains life on Earth. Now let's delve deeper into the different types of chemical weathering. First on our list is hydration, a fundamental chemical weathering process. Now if we strip down the term, we see hydro, which means water, and ation, which implies action. So, in essence, hydration is all about the action of water. But how does this work in context of weathering? Well, hydration involves the absorption of water into the crystal structure of a mineral, causing it to expand. This expansion often leads to physical changes in the rock, such as increased volume, and can result in the rock eventually breaking apart. It's like adding water to a sponge and watching it puff up, except in this case, the sponge is a rock, and the puffing up can take a considerable amount of time. A common example of hydration can be seen in the weathering of clay minerals. Clay, as you might know, has a remarkable ability to absorb water. This absorption causes clay particles to expand, and as they dry, they contract. This cycle of expansion and contraction over time weakens the rock structure, leading to its eventual breakdown. So to put it simply, hydration is a process where water is the star performer, working quietly and steadily to change the landscape one rock at a time. So the next time you see a rock expanding or contracting, you'll know hydration might be at work. Moving on, we have hydrolysis, another fascinating type of chemical weathering. Now the term hydrolysis might sound a bit intimidating, but let's break it down. Hydro refers to water, and lysis means to separate. So, in essence, hydrolysis is a process where water separates or breaks down other substances. This process involves a chemical reaction between water and another substance to form a completely new substance. It's like a magic trick, but instead of a magician, we have Mother Nature at work. This is not something that happens abruptly, but over a long period of time, and the changes are often so subtle that they're not immediately noticeable. To help us understand this better, let's take a look at an example. Consider feldspar, a common mineral found in rocks. When feldspar comes into contact with water, a hydrolysis reaction takes place. The water molecules break down the feldspar, converting it into a substance called clay. This is why, over time, you might notice that rocky landscapes gradually change, with clay-rich soil appearing where there once were solid rocks. This process is incredibly significant. It's not just about turning rocks into soil, it's about creating an environment where plants can grow, which in turn supports life. Hydrolysis, a subtle yet powerful process, significantly contributes to the transformation of our landscapes. Next up are oxidation and reduction, two chemical reactions that often go hand in hand. Let's start with oxidation. Picture this: you're walking through a rocky terrain and you spot a reddish-brown streak on a boulder. That, my friends, is the work of oxidation. Oxidation is a process where oxygen interacts with a substance, often resulting in a change of color. This is precisely what happens when iron in rocks meets oxygen in the air or water. The result? Rust, or to use its scientific name, iron oxide. It's this rusty color that gives many rocks and soils their reddish hues. Now, what about reduction? If oxidation is about the addition of oxygen, then reduction is its counterpoint. Reduction involves the removal of oxygen from a substance. It's like the yin to oxidation's yang. For instance, consider rocks containing iron or sulfur. When these rocks are exposed to certain conditions, such as a lack of oxygen or the presence of certain bacteria, the oxygen bound within them can be removed, a process we call reduction. Together, oxidation and reduction are part of a grand dance that shapes our world. They can weaken rocks, causing them to crumble, break, or dissolve. They can also lead to the creation of new minerals, reshaping the landscape over time. These processes are not just confined to the surface of our planet, but also play out deep within the Earth's crust and in the oceans, contributing to the dynamic nature of Earth's geology. In the grand scheme of things, these processes may seem slow and subtle, but their impact is monumental. Think of the Grand Canyon, or the rusty red soils of Prince Edward Island. These are not just landscapes, but the results of countless oxidation and reduction reactions happening over millions of years. Oxidation and reduction, although complex, play a crucial role in reshaping our Earth's surface. Last but not least, we have carbonation and solution, two vital chemical weathering processes. Let's first dive into carbonation. This intriguing process involves the reaction of carbonate or bicarbonate with minerals. Now you may be wondering, where does this carbonate or bicarbonate come from? The answer lies in the simple, yet omnipresent carbon dioxide. As rain falls through the atmosphere, it absorbs carbon dioxide, forming a weak carbonic acid. When this mildly acidic rainwater seeps into the ground, it reacts with minerals in the rocks, particularly those containing calcium, potassium, or sodium. The result? The formation of new carbonate minerals. A classic example is the formation of limestone caves. The carbonic acid in the rainwater reacts with the calcium carbonate in the limestone, causing it to dissolve over time. This gradual dissolution leads to the formation of caves, sinkholes, and other karst landscapes. So, the next time you marvel at the beauty of a cave, remember the silent and slow process of carbonation that has shaped it. Next on our list is solution, another process that may not be as evident to the naked eye, but is equally fascinating. Solution is the process where rocks dissolve in water. Yes, you heard it right, rocks can actually dissolve. This typically happens when certain minerals in the rocks are soluble in water. A common example is salt. Have you ever noticed how salt disappears when you stir it in water? That's solution in action. Salt rocks or halite, when exposed to rainwater, can dissolve, leading to the formation of salt pans or brine pools. Over time, this can significantly alter the landscape. It's also why we often find salt deposits in areas that were once covered by seawater. So, there you have it. Carbonation and solution. Two processes quietly at work, weathering rocks, shaping landscapes, and influencing the world around us. While they may not leave behind dramatic scars like some other forms of weathering, they are nonetheless vital in the grand scheme of Earth's geological narrative. Carbonation and solution, while less obvious to the naked eye, have a profound impact on our environment. As we've seen, chemical weathering is a fascinating and complex process. It's an intricate dance of elements and compounds driven by the forces of nature that can transform the world around us in profound ways. We started off with hydration, a process that involves the absorption of water into the minerals of rocks. This can cause physical changes such as expansion, and can lead to the weakening and eventual breakdown of the rock. A great example of this is the weathering of clay minerals, which absorb water and expand, leading to the crumbling of the rock. We then moved on to hydrolysis, a chemical reaction that involves water. In this process, water molecules can react with minerals in the rock to form new minerals and soluble salts. One example we discussed was the weathering of feldspar into clay. Next, we tackled oxidation and reduction. Oxidation, often called rusting, involves the reaction of oxygen with minerals, particularly those containing iron, leading to the formation of oxides. On the other hand, reduction, which is the opposite of oxidation, can occur in environments with little to no oxygen. An example of this is the formation of iron sulfides in swampy areas. Last but not least, we explored carbonation and solution. Carbonation involves the reaction of carbon dioxide with minerals, leading to the formation of carbonates. This process is particularly important in the formation of limestone caves. Solution, on the other hand, involves the dissolving of rock minerals in water. This is a common process in areas with a lot of rainfall and can lead to the formation of sinkholes and other interesting geological features. So there we have it, 6 types of chemical weathering: hydration, hydrolysis, oxidation, reduction, carbonation, and solution. Each of these processes plays a vital role in shaping the landscapes we see around us. Understanding these processes is not just a geological concern, but a way for us to appreciate the dynamic and ever-changing world we live in.